Thank you, the organizer, for allowing me to make this presentation. I'm Sophie, and I'm really glad to present to you my ongoing research with it, which is the upside-down motion in NGC 6231 towards sounding the internal structure of massive binary stars. So first of all, what is the upside-down motion? Well, the upside-down motion, as you can see in this animated view of a system, is the slow precession of the line of upside with time, which is basically defined as the time derivative of the longitude of periastron omega. So it takes its origin from the tidal interactions occurring between the two components of a system, which in turn induce that the stellar gravitational fields are no longer spherically symmetric. So it is mostly seen in closed short period eccentric system, and the upside-down motion rate depends upon the internal structure constant K2 of the stars, which is an indicator of the density stratification inside the stars. So this K2 value decreases with time as the star evolves because its core becomes more and more concentrated, while the envelope becomes more and more diluted. So basically, knowing the upside-down motion rate of a binary system gives direct insight into the internal structure of the stars, which is kind of valuable information, especially for massive stars. So if we know the stellar fundamental parameters of the stars, as well as the upside-down motion rate of a system, on the one hand, and if on the other hand, we have a stellar evolution code, whatever it is, then we can confront those two and put some physical constraint on the internal mixing processes occurring inside the stars. But if you mind, I propose you to stop here for a moment before entering into too much theoretical details. And let me raise a really down-to-earth question and answer to it, of course. How can we measure this rate of upside-down motion? Well, as you can see here, there are basically two ways of doing this. And at the upside-down motion rate is a very slow motion. Both methods need a set of observational data spanning several years, which might be quite challenging in practice. So the first method here you can see on the left panel makes use of a set of radial velocity measurement taken for a binary system at different epoch. And if we would try to fit a curve to these data, explicitly accounting for the upside-down motion through the variation of omega, then we can estimate this upside-down motion rate. So you can see here, the first set of data and the last one are separated by about 60 years. And you see a clear change of morphology here of the radial velocity curve, which is the sign of the presence of upside-down motion in this system. On the right-hand side, you can see here the second method, which makes use of a set of photometric data of the binary system. So we know that in an eccentric system, the depth of the eclipses depends notably upon the orbital separation at the conjunction phase and the depth at the most profound if it happens close to periastron passage. And the orbital separation itself depends upon the orientation of the ellipse with respect to a line of sight, that is to say, omega. So here we have plotted 9 theoretical light curves for a twin system, meaning that the two stars are identical. So we have plotted here 9 theoretical light curves for 9 different values of omega. And what we see here is the change in the depth of the primary eclipse and the change in the phase of the secondary eclipse are entirely attributable to this upside-down motion rate. So now that we have a better idea of how we can estimate this upside-down motion rate, how can we make the most of it to constrain the internal structure of the stars? Well, to this, we have to show here the upside-down motion equation of a system. So it is basically made of two contributions. We have a Newtonian contribution and a general relativity correction. So the Newtonian contribution is itself the sum of two contributions, the one arising from the tidal interactions occurring between the two stars and the one arising from the rotation of the stars. So very quickly in this equation, E stands for the eccentricity, F and G being function of the eccentricity, R are the radii, A the semi-major axis, Q the mass ratio, M the masses of the stars, P orb and P rod the orbital and rotational periods, and K21 and K22 the internal structure constant of the stars. These K2 are computed through the integration of the differential equation, the Clairaut-Rado differential equation, which depends upon the density inside the stars. So basically, in this equation, every quantity can be constrained observationally, except for the K21 and the K22. So this is what we do, and we are left with one equation and two unknowns. But in the special case of a twin system where the two stars are identical, meaning that they have the same mass, radian, and position in HR diagram, then we can solve this equation because K21 equals K22, and then we can get the K2 observational. In the general case, we unfortunately cannot do that, but we can make use of a small trick, which consists in computing a weighted average mean here of the K2 of the two stars, and we can solve this and get an observational value for this quantity. So this is basically what we have done for two binary systems belonging to the cluster I have mentioned before. So the first one is the twin system, meaning that the two stars are identical, as you can see here with their properties here. So for this system, we could compute a K2 observational. And what we have done is that we have built some stellar evolution models with the clay code, which is developed at our department in Liège. And we have searched for best fit models for the stars. So best fit in the sense that we had to reproduce the mass and position in HR diagram, and we used as three parameters, notably the age of the stars, the initial mass of the stars, as well as the turbulent diffusion. So here we accounted for the internal mixing processes occurring inside the stars through this very general turbulent diffusion form, which we insist on the fact that it might simply be the reflection of the stars, the rotation of the stars, for instance. So here in this HR diagram, you can see in green here a track that passes through the observation value in red. So this is the track that corresponds to the best fit models in terms of mass and position in the HR diagram. And as you can see, it has a certain amount of turbulent diffusion. In blue, for a comparison, we have a track which has no turbulent diffusion. And from this first observation, we see that we need to put some turbulent diffusion inside the models to notably reproduce the observational quantities of the stars. So over plotted on these tracks, the dots corresponds to the model having the K2 equal to the observational K2. And what we see here is that when crossing the observational box, the K2 of the model in green here is too high compared to the value it should have, meaning that the model has too low density contrast. So to overcome this difficulty, we build other stellar evolution models, and this time constraining not only the mass and position in HR diagram, but also the K2 value. And we ended up with a track here in orange that has a certain amount of turbulent mixing, which is higher than the green track. And we see here that the model in orange here passes through the observation. It's a bit further away from the exact observational value, but still within the error bars. And we now can fit the K2 value. So from this system, we can conclude that some enhanced mixing needs to be included in the models to notably reproduce this K2 value. So after that, we also studied another system, but this time the system is made of two different stars. So here we had to construct two different stellar evolution models for the two stars. And we could compute a weighted average mean for the K2. And as the primary star is the most massive one, we know that its K2 is smaller than the K2 of the secondary star, and we get this relationship. So let's look at the primary star here in the HR diagram. And in green here, we have a track that passes through the observation. And we see that this track, the model having the right K2 within the observational, within the error bars, sorry, here are very far away from the observational box. We basically know what we have to do because we have studied the system before. So we know we have to put some enhanced mixing inside the models. And we have here the track in purple and in orange. But this case, we cannot find any model that is able to reproduce both the mass and position in the HR diagram on the one hand and the K2 value on the other hand. So here we raise a question, and we kind of see that some physical processes occurring inside the stars are still poorly known. And in addition to that, we have another problem with this system. When considering the secondary star and looking at the track that passes through the observational box here in the HR diagram, with the blue track passes very close to the observation here, we see that these models, which reproduce the parameters, the stellar parameters, have an age of about 26 million years, while the ages of the models that best fit the primary star have an age of 9 million years, which is quite incompatible, seeing that it's a binary system. So here we also have some further investigation to be done to try to understand why we have such a discrepancy between the two stars. So from everything I've said the last few minutes, I would like to leave you this takeaway message that from the analysis of the upside-down motion in massive binary stars and its link to the internal structure of the stars, we arrive at the conclusion that the standard stellar evolution models have a too low density contrast, and that to reproduce the K2 value of the stars intably, we have to put some hand-hands mixing inside the models. And secondly, if one wants to perform such an exercise, the best candidates are the twin systems, for which we can solve the upside-down motion equation for the K2 value. And these are the systems for which we can expect to get the most valuable information regarding the massive stars. So I would like to thank you for your attention, and I will be glad to answer any of your questions now or later. Thanks.